Hi, and thanks for watching this video about sketching the graph of this rational function. Okay, what we're going to find out is this rational function was going to have a hole in the graph, also known as a removable discontinuity. And we'll talk about that as we get closer to figuring that out. So we're first going to start by putting on some axes here. I'm going to put on a y-axis and an x-axis. And we're going to figure out the four basic things for any rational equation. Number one, the vertical asymptote. So we find vertical asymptotes from our denominator. We have to set your denominator equal to 0. So if we set x minus 3 equal to 0, I find that I have a vertical asymptote where x will equal 3. So I come over here and I put a dashed line to represent my vertical asymptote. Okay. Second thing I look for is the horizontal asymptote. Okay, now this is determined by three different things, and that is called the degree of your numerator and denominator. So we notice that the degree on top is a 2, and the degree on bottom is a 1. So we have a quadratic on top and a linear equation on bottom, which means this equation is what we call bottom, or rather top-heavy. And a top-heavy equation has no horizontal asymptote. Okay, and we could calculate its oblique asymptote, but let's hold off on that for a second. So now we're going to figure out what the y-intercept, where will this thing cross our y-axis? So to do that, we plug in 0 everywhere for x. So 0 squared minus 9 over 0 minus 3 becomes a positive 3. So our graph will cross our y-axis at positive 3. And finally, the x-intercept that we do by solving the numerator. So x squared minus 9 equals 0. X squared equals 9. So x is positive 3 and x is negative 3. Okay, and this is where the red flags start flying. We have an x-intercept at positive 3, but we also have a vertical asymptote at positive 3. So that should be the first sign that this is a very strange graph, because we normally don't have intercepts where we have asymptotes, because that's just shouldn't occur. It can't cross the axis where there's supposed to be something where it can't cross. So that's actually where we're going to find our hole, or your removable discontinuity. So what we're going to do actually is come back up here to our original equation, and we're going to factor the numerator into x plus 3 and x minus 3 over x minus 3, and you'll notice that the x minus 3's divide out. Divide and give you a 1. So that means we're left with, sorry, that's a plus, basically the graph of y equals x plus 3. Okay, which is a nice linear equation that crosses, well, that goes like this, our nice linear equation. But what's strange is that when we get over here to where it would have been positive 3, instead of having the graph continue, this is where we find your hole. Okay, and of course the graph continues up through there. So this is what the graph looks like. When we cancel, when the denominator divides out, okay, as we just saw that it did, it factored to x plus 3 on top and x minus 3 on bottom. So when the x minus 3's divide out, we're left with a linear equation. So we don't really have an asymptote anymore. This is no longer an asymptote, because the graph doesn't go to positive and negative infinity. And I don't know why am I here. This one work. Anyway, it's not working. I'm going to have a hole where x is positive 3. So the graph will continue on everywhere. Continue, 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 continue until it gets to positive 3. We have a hole, and then it continues on everywhere after that. Thanks for watching.